Okay. Okay, so again, welcome. We talked last time, the first class, we talked about the Simpson paradox and about some example motivating causal reasoning. That's the subject of the class. And we will continue today. We started with causal hierarchy. I will pick it up from there. And this we already we covered, so I gave you some examples. But before I start, maybe you let me ask if you have any questions. Logistics about the class. Remember, this is a seminar. Most of your participation would be by presenting some material, some papers or chapters, and doing a project, and there will be some homeworks. And that's basically it. Anytime you have a questions, please say. I'm happy. It will be see some new faces. Hi Vincent. And if you have questions, just call. So we talked about this idea that we need to model the world by some assumption about causal reasoning. And this, one of the things that was introduced by Pearl was this ladder of causation, this three-rung ladder. So going over it, these three different activities that we are engaged in connection with data: seeing, observing what is going on in the world, doing, namely intervening on the world, and also imagining. We are, as human beings, in contrast to animals, I believe, we are able to imagine worlds that we are not existing at the moment. And this is associated with these three ladders of causation. The first one is association. And it's just our activity is seeing, observing, and we ask questions about what happens when I see something. How does it change my belief? We ask whether a symptom is indicate that we have some disease, or what does a survey tell us about the election results. The reason that I'm bending like that is that I see everything very small on my screen. I'll try to really, for the future, to be able to see what the slides also on the big screen, but right now it doesn't work for me. Anyway, so this is the problem at my end. So this is the first level, and this is the level where we think the animals operates, and the current machine learning advances are at. And then there is the level of intervention of what if I do something, what will happen? And this is what will happen if I take an aspirin, if I take a drug, and stuff like that. We change the world, we intervene on the world. And the last one is counterfactual. So let me move something here. Cannot see my screen. We'll do this. Okay. So so as I said, the top rank is counterfactual learners. We can imagine the world, and we can imagine worlds that do not exist. And this information, the causal information that we capture, as we will see by structural causal model, will allow us to really reason in that world. So for example, what happened, a typical question is, what is, was it the aspirin that stopped my headache? So we took an aspirin, the headache was gone, but we really want to know is, would it go away without the aspirin as well? So something happened, we saw the consequences of what happens on the world, and we are hypothesizing what will happen if we took a different route. When we wanted to go from X to Y, we took one route because we must make a decision, and then we ask ourselves, could it be better at a different route to the same location? So counterfactual is what we engaged in a lot. And the point of making this distinction between ladder rank 1, rank 2, and rank 3 is that you cannot, the point is, you will not be able to answer queries of intervention just by associations, just from data. You will have to really consult the structural causal model that makes additional assumptions about the reality. And likewise, counterfactuals, you need something extra. You cannot just answer counterfactual questions when you are restricting yourself just to a do operator, as what we will see later on. So these are the three letters of causation that we started to talk about last time. And now I will give some just additional illustration for examples of these three type of activities. So suppose, let's look at this, the firing squad. This is a story appearing in the Book of Why. Suppose that the prisoner is about to be executed. First, the court has to order the execution. The order goes to a captain who signals to the soldiers on the firing squad and to fire, and they fire. So that's the story. And we can capture it. We already saw that not on an intuitive level, that we capture these ideas of what causes what by directed graphs. So here we can capture the story in this graph that we have here. See, we have 5 variables. Each one of them has 2 values, yes or no. CO's court order was received, yes or no. The captain instructed the soldier to fire, yes or not. A fired, B fired, yes or no. The prisoner is dead. So that's the information. And now we can, and in the letter 1 query, we can ask, we may observe that the prisoner is dead. Observation, and we can ask, what does that mean that the court order was given? What do you think?
Not necessarily, unless you have like exogenous variables that might have happened, right, to have killed him. So like suppose he gets struck by lightning, for instance.
Okay, but the model, this, you're right, that could be some assumptions that we are not making, but now in this model, I'm making stricter assumptions than what you are suggesting. I'm assuming, no, it doesn't happen. I'm assuming a model where for sure things are deterministic, everything is logic-based, and you can make this assumption, and based on this assumption, what would you infer if you see the prisoner dead?
Yeah, I would infer that the court order was given.
Yes, exactly. So we are making an assumption, and this is the assumption, and yes, we use logic. Let's say that alternative, but the point is, it's a query of the type that you are making just by observing the world. And suppose we find out that A fired. That's another observation. What does that tell us about B? Again, under the same assumptions. Did B fired or not? Given the assumptions we make about the world.
Yes, because the captain would have had to have given the order for both of them.
Exactly. So this is just an illustration under these assumptions about the reality, what we can answer when we observe. So now let's look at a different query, which is in rank 2, we can ask questions of intervention. So what if soldier A, now we are asking, what if soldier A decides on his own initiative to fire without waiting for the captain's command? Will the prisoner be dead or alive? Anybody? Anyone?
I can answer again, but I feel like I've done a lot already.
Yeah. Anybody else wants to volunteer, say something? This is simple. The answer is yes, of course. And we can think about what the kind of reasoning that we are doing. Okay, let's reveal that there is what is going on here when we are doing the intervention. A is deciding to fire, is that now this variable A is set to true, and it doesn't matter what happened, whether there was a court order or not. So the model of the world now becomes, given the intervention, we remove the influence from the captain. And from this model now, the intervention is illustrated by removing these connections and setting A to true. And from that, because we know the functions associated, I told you in words, I didn't say, I didn't model it in logic, but you know what it means, then obviously the prisoner will be dead. That's what we can infer from that. So that's so this will, but this required what I did. It required this changing the model to really determine that and to make this inference. And this is something that we are doing that corresponds to really what we will do for a query of intervention. And let's continue now with a counterfactual query. Suppose the prisoner is lying dead on the ground, okay, you see it. And using a level 1 query, it implies that A shot, B shot, the captain gave the signal, and the court gave the order. So we know that. Now, in contrary to fact, A had decided not to shoot. Would the prisoner be alive? So we have the reality of what had happened. And now we are asking a hypothetical question or counterfactual question. If contrary to what we observe, what would have happened if A had decided not to shoot? Would the prisoner be alive? I mean, what do you think? Anybody, including Bruce, anybody? Yes. I don't see you, so I mean, just talk.
The prisoner would be living, right? Model assumes that he shoots after, if he dies because he gets shot.
Yes. So what? So he will still be dead, right? Because I mean, is that the answer?
Yeah, he should still be dead, because even if A decides not to shoot, the court order was still given. The captain would have ordered B to fire, and B would have fired.
Yeah, exactly. So we know that the captain gave the order because the prisoner was dead. So we infer from the reality what happened, and we can now look at the again in the fictional world where we are asking the questions in. Again, we are making a not shoot. We are asking not to shoot. So we can infer from the first world, the true world, that B shot, the order was given, and so on. But now we are we intervene on this world and we set A to false. We remove this arg, and still, because of the function that we have here, that it is enough that one prisoner will shoot to make the prisoner dead, the one soldier to shoot to make the prisoner dead, and we can infer this counterfactual query. So it requires reasoning on two worlds, on the real world and to imagine a different world. But the imagined world is already fed from the data that we get from this the real world. So the fictional world is fed with information. So it requires much more, and it really represents difficulty to statistics, the ability to reason in two worlds. And so the point is that these are different level of queries, and they require the third ladder, the third rank. So in the France, for example, we ruled out, okay. So as Bruce mentioned, I mean, there could be interference, there could be noise, and there could be exceptions. We are not modeling it here in this particular example, but obviously there are examples where you will have uncertainty. So maybe the captain gave his order a split second after Rifleman A decided to shoot. So maybe he decided to shoot, but the captain still gave an order. So there are all sorts of small probability worlds, things that can exist and exist in the world, and we want to accommodate them in our modeling. So we have to use uncertainty. So here is another example, smallpox vaccination, where we can see some illustration with uncertainty. It's very timely. This is actually happened, presumably, in the smallpox disease a long time ago. So suppose that out of 1 million children, 99% are vaccinated and 1% are not. If a child is vaccinated, he or she has one chance in 100 of developing a reaction, and the reaction has one chance in 100 of being fatal. On the other hand, he or she has no chance of developing smallpox if they got the vaccination. Meanwhile, if a child is not vaccinated, he or she obviously has zero chance of developing the reaction to the vaccine, but he or she has one chance in 50 for developing smallpox, and smallpox is fatal in 1 out of 5 cases. So we can think maybe that the model and this story would correspond to this diagram here. And let's now, this is the underlying assumptions about the world that we can assume. And now we have data. And the data says that indeed 1 out of 1,990,000 get vaccinated. From them, 9,900 get the reaction, and 99 die from the reaction. Meanwhile, 10,000 don't get vaccinated, 200 get smallpox, and 40 die from the disease. These are according to those numbers. So what we see here, that more children die from vaccination, 99, than from the disease, from the data. So this was an example, maybe simplified, but people pointed to it and said, oh, we shouldn't get vaccinated. More people are dying from vaccination. So I'm sure that you know what is flawed in this rationale, reasoning. But in order to do that, I mean, obviously it's much better to be vaccinated given this data that we have here. But we can now ask, in order to pinpoint what is the issue, we can now ask the counterfactual question. What if we had the vaccination rate to 0? Namely, nobody would be vaccinated. What would have happened then? So that's a counterfactual query. And we can conclude immediately that out of the 1 million children, 20,000 would have gotten smallpox, 4,000 could have died, which is many, many more than what we had in the actual scenario. So by having this ability to pose counterfactual queries and now to use this model that we have, causal model, we can address this question. Here, what is the information here that we got from the real world? Do you think? I myself, I'm not sure. What is it? I speculate. Yeah.
So you're asking like what's the actual outcomes, right?
We have a story about the real world, what had happened. And
Yeah.
now we ask hypothetical questions. What would have happened had the vaccination rate been 0?
Mm-hmm.
And in the previous example of the fire squad, what was the main point is that you can infer something from the real world. What is it that we can infer from the real world here?
So if you were to go with the real world data and just like use that as your decision-making process, you should say you wouldn't get vaccinated because you have a higher chance of dying, right?
Yeah, but the question, yeah, you're right, and this is what we want to show, that it's a faulty reasoning, because obviously there were. If we didn't vaccinate anybody, that would be worse. But I think what you get, because you can argue, well, once I have the model, obviously I can just plug the vaccination, the data, any data the number of vaccinated people rate to be 0. I can do it without seeing the data even. I can do it once I'm making the assumptions. So in this case, I think what you can argue you get from the data is the rates. The story is not being told that way. We are being told what are the rates. But if we didn't have the rates and we get some information, we can infer what are the probability or the ratio of people being vaccinated and getting the reaction from that, and then we can choose a different world in which only 0% are vaccinated. In this case, the vaccination variable is at the root, so there is nothing to cut. But I think what the point of this example was meant to show that things can be extended and should be extended to accommodate noise and probabilities. Okay, so in summary, the big picture of this Perel's causal hierarchy is that we have these 3 ladders. Let's the ladder with 3 rungs. The first rung is association, and we ask queries about what is the probability of y given x. These are the type of question. How would seeing x change my belief in y? And the example is that we saw what does a symptom tell us about the disease. The second rank, what happens now? Okay, is intervention. We want to ask the question, what will be the probability of some variable y if we do x, if we intervene on the world? It's not seeing, it's doing. What if I do x? And the aspirin example was the one that we gave. And finally, counterfactual. And counterfactual requires imagining and retrospection. And these are questions of why. What if I had acted differently? And the way it will be formalized, it will by this kind of variables that I will allow you to have the action take 2 different variables. So we have x prime, y prime, which is what we stands for x and y, what we observe. But we want to know what had happened had we done x, which is a different value for this variable. What we now have in computer science, in artificial intelligence, we have mostly work in rank 1, in the association level. This is deep networks, this is Bayesian networks, in contrast to causal Bayesian networks. But if you took my class on Bayesian network, we look at them, or graphical model, as such a decomposition ways or factored ways for representing probability distributions, namely what is going on in the world. In doing, this is what we will focus on here. You can think in reinforcement learning as trying to address this issue. In machine learning, causal Bayesian networks, when we add semantics of causality to Bayesian networks, Markov decision process, and so on, they can be attributed with causality. And finally, if we really want to do counterfactuals, it's not enough to stay in causal Bayesian networks even, or MDP, PoMDP. We have to have structural causal models that I will define shortly.
So I have a question. So has anyone actually done work at seeing like if in a reinforcement learning model, there is like an equivalent, cognitive mechanism to the do operator and how the model processes information? Because like this is the first time I've seen this claim that we should think of reinforcement learners as really learning to do intervention, right? Which is actually really cool. I find that seems intuitive and plausible, but like, has anyone actually looked at this and say, okay, like what's the part of the model that does it, you know?
Yes, so I don't have, I think will be an opportunity, this class, to be exposed to this. I know that some people are working on it. By the way, I didn't say it explicitly, but some of my slides are, many of my slides will be taken from Elias Birnbaum, who is a Pearl student that is a professor at Columbia University, and he is working in this area. He has several papers about reinforcement learning from the causality perspective. So it will be really interesting to look at his papers. And I think maybe the work that you saw could be his work. I don't know.
Yeah, I would actually be interested in like presenting on that, because that sounds really fascinating.
Yeah. So there is now work going on to incorporate causal reasoning in machine learning. So there is a beginning of that, but most of the machine learning work and the AI work treat it implicit, either doesn't treat it or treat it implicitly. So we are here because we want to move forward. It's clear that we need to have causality in order to move forward to be able to capture human intelligence. There was a citation that I gave, but I didn't say anything about it. There is a paper by Adnan Darwish from 2017, where he talks about animal intelligence versus human intelligence. His article is geared into trying to advocate that function approximation, the main thing that is going on in neural networks in learning community these days is cannot capture human intelligence. It will definitely be in the level of association, but it's even worse that because it's really a black box kind of representation, while we still, even at the level of association, we have representations and symbolic representation that can go and provide explanations. But this is a good point, and we can continue to talk about it. But let's move on, and unless you have another question.
No, thank you.
Okay. So now let's see what structural causal models are. We will now give a definition. They will get more and more formal. It's actually very simple. But in order to talk about structural causal model, we need to be able to talk about, to clarify some graph concepts. We will be talking about directed graphs. And in directed graphs, we can talk about the notion of parents. So every node will, all the nodes pointing to it are its parents. So B has A as a parent, C has B as a parent, D has A, B, C as parents. We will also talk about ancestors, which will not necessarily direct parents, but the parents and the parents of the parents and so on. We will talk about children, which are the direct nodes that a node point to. So the children of B are C and D. These are all concepts I'm sure you know. Descendants, again, is the children and the children of the children and so on. We will talk about the notion of a path, and directed path. So directed path are obviously we have A, B, C, D. The path may not always be directed. We may talk about path when we ignore the directionality. So when we say path, it means any path regardless of the arrows themselves. We can have cyclic graphs. So in this example, we can go from A to D to F to A. We have a cycle, or acyclic graphs like the one here. And in all our definitions, we will assume that we are working in directed acyclic graph, no cycles, no directed cycles. There are cycles, but they are not directed. So that's the graph concept. And here is what structural causal model is. So it's a model M. And the idea is that it describes the world. And this describes what we know about the world. So there is the true structural causal model that exists in the world. And there is our model, which is capturing only part of it because we don't know the whole world. So, and it will be, it consists of two types of variables, U and V, and a set of functions. So it's a triplet, U, V, and set of function. Each function assigns value to a variable in V based on the values of other variables. We say that variable X is a direct cause of Y if it appears in the function of Y. So each variable will have its own function, and all the other arguments will be called its causes, direct causes. And now U are designated for exogenous variables, which are external to the model. We do not explain how they are caused, and they don't have parents. Variables in U have no parents. So here is an example. Let's assume that we are talking about salary, how salary is impacted by the number of years in school, a number of years in practice of the profession. And let's assume, so we have Z is the salary, and X and Y, we regard them as exogenous variables that we may not know their value or how they were generated. And the function that we have is that Z equal to X plus 3Y. We are talking about, we are making, this is how the world, we assume, is operating. So this would be, this will be a structural causal model. Now we want to associate this structural causal model with a graph. And the graph of a structural causal model contains one node for each variable in M. And if in M, the function f associated with x for x contains variable y, we will have an arrow, an arc. Namely, x depends on y for its value, then there will be a directed edge from y to x. Okay, so you can see the graphical model for our example here below. And the graphical model of causation, so a graphical definition of causation is that if in the model, in the graph, variable x is the child of variable y, then y is a direct cause of x. And if x is a descendant of y, then y is a potential cause of x. So there is a distinction between a direct cause and a potential cause. Okay, so that's the definition. And let's see some more illustration of this definition. Again, this is from the primer book. Suppose we talk about three variables: the performance in basketball of a player, his height, and his sex. These are the three variables, the visible variables, V. And for each one of them, we have some other exogenous variables, one for each. And we have two functions. So sex is just a function of this exogenous variable U1. It is X. So we assume that all the variables here has values true and false. No, actually sex is male and female. Height will be actually numbers, but we can discretize it or not. And no, I'm taking back the true or false. In this example, it's continuous actually. So we have two functions: the height as a function of sex and some error function, or error variables or unknown causes that we are not specifying, and the performance is a function of both height, sex, and some exogenous variables. So you are unmeasured terms that we do not care to name. Random causes we do not care about. You are sometimes called error terms. So this could be our graph, the graph associated with this causal model. Any questions?
So I know that so I guess this is a more advanced question that we'll eventually get to at some point. I was thinking about knowing when your causal model is accurate to reflect the underlying actual causal dynamics of the system you're modeling. I know that sometimes if you have confounders between your variables in V and your variables in U, like not in that ways not specified by your graph, right? That is typically taken to be indication that you've not accurately modeled. Is that correct?
Yeah, in general, yes. So there are, the causal model that you are assuming is an assumption, and there are ways of checking consistency with reality. So for example, and this people who are working in causal discovery make use of that. So you can, when you have, and we will get to it shortly, when you are assuming a structural causal model, you're assuming conditional independencies that comes from the graph associated with the data. So if the data that you see is inconsistent with those assumptions, you know that something is wrong in your model. This is one way, one primary way of knowing that something is wrong with your model, and you need to revise it. So definitely the issue of how to check whether your model is consistent with everything you know or not is very important. So we will assume, when in many of the cases, we will assume, let's assume that our structural causal model, which is a partial model of reality, we never have the true model of reality. We can think about the true model of reality being some kind of structural causal model, and our knowledge will be some graph that we think is consistent with the model, with the world, and hopefully it is consistent, and maybe we have ways of checking that, yes. But for now, we are assuming that the main thing is that we write what is our structural causal model, and we can now examine whether it makes sense and what we can infer from that. And we will get to it. To the task of causal discovery, we will get later on in the course. So let's say more on exogeneity, endogeneity, exogeneity. How do you say exogeneity, or how do you pronounce this?
Exogeneity.
Exogeneity and endogeneity. Okay.
I believe so.
Okay.
Anyone else, if I'm wrong?
Okay. Okay, so just some more examples that I have, some slides. I took my slides. I have some of the slides I made, but many of them are from Elias Barenbaum. Others are from a class for high school students that was taught based on the primer book. And those are very nice slides. Sometimes you can recognize them by the fact that they describe things in detail. So what are exogenous? And this is just an example. We can designate the variables that are not, they have no parents as exogenous. In this case, we designate A, E, C, we say they are exogenous. The endogenous variables are, in this example, will be B, D, F, G, E. The function and their inputs. Now, from the graph, we know what, I mean, the directed acyclic graph calls for certain functions that needs to be specified. Sometimes we will specify them explicitly, and often we will not. We just will assume that there is a function that for G, which is endogenous variables, what will be the function. So for A, we don't have any parents, so it can be arbitrary. No functions for exogenous variables. For B, we have two parents, C and E, so it will be functions of B, its values as a function of its two parents. D will have four variables determining its value, and so on. So just another illustration. Okay, so we will come back to that and see more illustration, and we'll talk more about properties. But one thing that is important is to realize that this structural causal model implies probability distribution. In general, in a structural causal model, we will assume that the functions are deterministic. They are all functions, but the uncertainty is on the exogenous variables. So there is a probability distribution on the exogenous variables, which implies a probability distribution on the endogenous variables. And because of the structure, which implies certain conditional probabilities that we will talk about, it's possible to show that the probability distribution associated with the variables can have a product form. So let's just talk about joint probability distributions. If we have two variables, in this case, X and Y, X is the color, the eye color, and Y is hair. They have several values. If we want to write the joint probability distribution, we will have a table for all the combinations of values. And clearly, if we have, the number of rows will be the product of the domains. And if we have many variables, it's not possible to specify a joint probability distribution. And this structural causal model, like Bayesian networks, if you took such a class, really help. So they lead this product form, and this is the product form. It will be, if we have a structural causal model, and we can imagine, in the case of Bayesian causal model, that instead of the functions, we insist on functions here. This must be functions for the structural causal model, but we can relax that and say, well, let's have it conditional probabilities. I mean, not 0-1 function, but probabilities saying what is the probability of the child D given all its parents. And in that case, which is a special case of the structural causal model, or vice versa. It's actually, it seems to be more general. Yes. Then we can express the joint probability distribution as a product of child given parents, which is a huge saving. And for instance, if we have this graphical model, in this graphical model, we will not have a lot of saving, but this is the decomposition. This is the Bayesian network. This is how the joint probability can be computed by the product of the probability of X, probability of Z, and the probability of Y given the two parents X and Z. And it's important because it saves us a lot of resource, writing the probability distribution and working with it. So for illustration, if you have never, if you were not exposed to Bayesian network, if we have this chain, eye color, age, and hair color, let's say Y point to X, X point to Z, we need only to specify the probability of y, then the probability of x given y, the probability of z given x. So instead of specifying this joint probability distribution that will be require 6 times 7 times 8 rows, it will take far less. All this, I'm sure, is really well known to you. If not, I mean, please consult any book. But we basically, what I said is enough. Any questions? Okay, so this allows us to get over the curse of dimensionality. Instead, if we have 5 variables instead of having 31 entries. And one of the issues, it's not only specifying, it's if we are doing sampling, for instance, if you get 100 samples from a distribution and you want to really estimate each one of the configuration of these probabilities, you will not have enough samples, enough data for this sampling. It will not be reliable, variance will be huge. While if we are estimating just these small entries, that these pairwise conditional probabilities, we have much more information per bucket, per configuration. So 20, on the average, 25. So again, this is a slide for these high school students that is really very nice, illustrating what we need. Any questions? So the connection with the product form Bayesian network is important, very important, and I will elaborate on it more.
So I guess another way to put it, what you're saying about one of the advantages of structural causal models is it provides us a way to factor our joint probability distribution by making certain conditional independence assumptions between our variables, right?
Exactly. Yes. So yes, and if it can be proved. What? I didn't. Somebody is talking, maybe unintentionally or intentionally. Was there any other question?
Yeah, I had turned on my microphone to ask a question, but I was waiting for the question to finish.
Okay, let me finish. Just say yes. And this, if you specify your model functionally, as we said, the factorization is implied. It's not an additional assumption, but you can prove it, that this factorization, it comes from the chain expression. And it's easy to show that it factorizes as I showed. Okay, what is the question that you asked?
So in that page where you were showing parents in structural causal model, I think the last slide section.
Which slide? I'm going back.
The last slide with the graph. The last slide with the graph.
Okay. This one?
Yes, this one. Yes. So here the function for D includes E as well. Sorry, C as well, even though C is not a direct parent of D. So do we include ancestors?
No, C is not. C will not have a function. It is. I mean, if it is.
I'm talking about FD. The function for D. Has
D
C
for D.
Well. Yeah. Has
yes.
C as well in it.
There's an arrow going from C to D. It might be obscured by your.
I didn't see that. Okay, fine.
Yeah, there is an arrow from C to D, direct arrow.
Okay.
So yeah. Actually, D has four parents.
Yeah, go ahead.
Yes. Mm-hmm. Yeah. So, I mean, to really, if you've never been exposed to Bayesian network, I will put it. You should read. There are two current textbook that are very good. One is by Adnan Darwish that I use in my class when I teach it, and one is by Kohler and Friedman, and both of them, or you can just look at Wikipedia. It can give you enough information. You can also look at my class page. I teach it. It's called 276, and you will find a lot of information. And just the first week will expose you to the main aspect of Bayesian networks.
When do you typically teach that course? Is it in the fall or winter or spring?
I taught it the last time I taught it. It was 2 years ago. So I teach in the fall. I taught constraint networks. In the previous spring, I think, or this previous fall, I taught the Bayesian network class. So if you look at my classes, I can answer also. If you send me an email, I will give you the exact link. Yeah, definitely write to me, and I will try to guide you. But this is, I will teach the necessary information. For instance, I'm going to talk about deseparation, which is essential for structural causal models, but it's also part of Bayesian networks, how you can decide what is conditionally independent on what based on just the graph. So the essential things I will definitely cover. This will be probably next week or Friday. We'll see. And but to fill in the gap, there are several textbooks. Also, I have a book, a shorter book that is called Probabilistic Deterministic Graphical Models that can also be used for that. So I'm not sure what would be the best.
If I remember right, we did like a couple weeks on Bayesian networks in 271.
Okay. So if you took test 271 with Caleb Kask, did you take it?
Yes, I did.
Yeah, definitely. Yeah. So also there you have the needed background.
There's also a concurrent course on graphical models going on, I think.
There is for many years. So this is a whole area. So there is Uncertainty in AI, UAI, which is the main conference for probabilistic graphical models. It started in 1985, and it's a yearly conference. And that's where most of the work now on this and in NeurIPS, where most of the work on probabilistic graphical models, but obviously, like everyone, there is a shift to machine learning and to neural networks and to combinations. But we will see papers. So papers on causality, I think, are published either in UAI or in NeurIPS or in the general AI conferences, which are ICHCAI or AAAI.
Yeah, I was actually mentioning that there's a concurrent class on course on graphical models that is being offered this quarter.
Where?
CS272, I think.
Say it again.
So there's a concurrent course being offered for graphical models this quarter.
It really.
You're saying there's another course that's being offered right now on graphical models?
In computer science?
Yes, CS272.
In learning in graduate course or undergraduate?
Graduate course.
Yeah, there is, could be by Eric Sadher.
I think it's by
learning, so it is focused on learning in graphical models, I think. Yeah. So the course that I'm giving is focused on reasoning with graphical models. It's more emphasis on algorithms and how to answer queries, assuming you have the model, you have the Bayesian network. I think he is focused more. But there is definitely, this is a good background. If you are taking that class, it will help you.
Okay, and I had one more question. From the description of structural causal models, I don't see what is the difference with respect to Bayesian networks, given that they are both being represented as products of condition probabilities.
Okay, so I will talk about it. The difference is that Bayesian network represent probability distribution. They are not assuming any causal interpretation. And the graph for the same distribution, for instance, if you have just a chain Bayesian network that represent the probability distribution. You can represent the same distribution by just reversing the arrows. And that would be okay for Bayesian network. It will not be okay for causal Bayesian networks. And I will definitely talk a lot about it.
Okay, cool. Thank you.
Well, okay, so see you all on Friday.
All right, excited to.
Bye.
Actually, I had one question for you,
Yes.
Professor Dechter.
Yeah.
You mentioned the work on RL and do operators. Could you tell me the name again so I can write it down? Because I want to look this up.
You want that I will tell you the author?
Yes.
He's on our website because his name is Elias Barenboim. And on the class website, one of the articles of PCH he's an author of this class, and he is also And so if you just will look at his website, I think you will find what you want.
It's one of the authors.
Yes, Elias Barenboim.
I see. Yeah, I see his work. PCH. Yeah.
Yes. And actually, the slides that I'm using is from many of them are from the class that he taught last semester.
Very cool.
Yeah.
Yeah. I'll look up his stuff. Thank you so much.
Sure. Okay. So see you Friday then.
Excuse me.
Yes.
Are you uploading are you uploading the recorded session on Canvas?
So it's on my website. So in Canvas you can access the class page. Let me stop recording and we can continue talking. I just want to be sure. Do you want to stop? Yes.